Morning, everyone. Can we have a little bit of silence, please? Good morning. Welcome to the usual IvS seminar. So today's seminar will be given by Vincent. So Vincent is a very local person here. So he did all his studies at KU Leuven. He got bachelor in math and physics, right? And he also got master in physics and astrophysics. So I wonder what's going to be, well, next one is going to be PhD, of course. So as you can see, Vincent is going to talk about astroseismology today, and I think it's going to be a little bit more on the theoretical side. I guess on inversion techniques, but of course Vincent is a better person to tell you what it is going to be about. So the floor is yours, Vincent.
Thank you, Andrew, for the introduction. And indeed, I will be talking about inversions as well as some other things I did with asteroseismic modeling. Before we go into the details of modeling techniques and such, let me give first, let's set some context. I'll start sort of with a question, namely, what is a star? You might think of a star that's an object in space. It has nuclear reactions going on inside it. It has all sorts of hydrodynamic, magnetohydrodynamic things going on. There might be multiple of them together. It might have a funny shape, deformed by rotation, etc. However, when I look at the star in my computer, it does not look like this. It looks like this. It is a simple line without any rotation or magnetism. It may have some simplified hydrodynamics. And you might be wondering, why is that? Why is this star that is that I see on my computer screen, why is it so different from the star in reality? And the reason for that is that stars are really complicated. My computer cannot handle a real star. Even if you go to a supercomputer, you will still spend countless hours of computing and maybe be a couple of years further in the life of the star. So we need to make approximations. The issue is those approximations come with parameters. We don't know exactly what is going on all the time in a star, so we parameterize certain aspects. So that means when we model a star, when we try to understand the star, we not only need to fit the fundamental or initial parameters of the star, like its mass, its composition, what was its initial rotation, what kind of magnetic field does it have, but also a whole bunch of parameters with regards to unknown physics, like how does the element transport in the star works, how was angular momentum transport works. As we saw last week as well, wind physics is also something that's parameterized, that you have laws for, that need to be tested observationally. So if we want to model a star, we need to take all of these things into account. Today, what will I be talking about? I will be talking, first of all, I will give an overview of the current asteroseismic modeling techniques. Then the main portion of the seminar will be about the pulsator HG192575. I'll try to explain how we try to get the rotation profile of this star and the properties of its magnetic field. And finally, I will give an overview of what my ongoing work is on structure inversions. All right, astroseismic modeling. What is that about? If you have a star, there are multiple mechanisms that excite waves in those stars. You can have turbulence, you can have certain layers in the star that effectively act like a heat engine, continuously contracting and expanding, and that generate waves. It's like if you have a violin here, if you take a bow and strike one of the strings, then there will be waves starting to travel along that string. But not all of those waves survive. There are only the waves that are the resonant frequencies of the star will actually be the ones that we observe. Well, at least if we talk about the type of modeling we here are going to do. So those observed frequencies, those can tell us something about the stellar structure. Why is that? Because this mode selection process, where only the resonant frequencies survive, depends on the structure of the star. If you change your structure of your star, then different frequencies will eventually be observed. So we can use the observed frequencies of the star to learn something about the internal structure. There are, of course, other constraints that we take into account as well. If you have spectroscopy of your star, then it will be useful as well to put limits on the temperature of your star, the surface gravity. Maybe if you have Gaia data, then you can also look at the luminosity of the star. The first technique that we use in order to actually do the modeling, so to go back from the observations to the stellar structure, is called forward modeling. And I'll give it a different name here as well. I'll also call it evolutionary modeling. That means that we take a whole range of parameters, so both those fundamental parameters and the unknown physics parameters, and we have a range of those parameters. Each of these parameters have possible values, and we compute a model grid. For each combination of parameters, we let an evolutionary model run from the birth of the star till whenever we want to. And then at each time step, we save a snapshot of the star, and for each of those snapshots, we can then compute our observations and compare them to the actual observations. And in that way, we can fit then and obtain the stellar parameters, both those initial parameters and those unknown physics parameters. This allows you to recover, first of all, those initial fundamental parameters, but is limited by the simulated physics. If the star is doing something that is not in your evolutionary model, then the parameters you get out of your fitting procedure might be completely wrong, or at least somewhat wrong. Here is an example of such forward modeling. This is the output you would essentially get. Each dot on this plot here, like all of these dots here, represent one stellar model at one point in time. And you can see here what were the parameters that were fitted. We have the initial mass, the initial metallicity, the age of the star, here shown by the core hydrogen fraction, and this FCBM, so it stands for convective boundary mixing, tells you something about how strongly is the material mixed near the convective core. And as you can see, there's all sort of correlations between these parameters. You can try to figure out what is the best model, here indicated by the star. So the yellow ones are the better models, the blue ones are the models that fit less well. And you can then try to put uncertainty regions, get uncertainty regions for your parameters. You can see here as well, included here is spectroscopic and Gaia constraints, so both on the luminosity and the effective temperature. And so this is a typical output you would get. You would get essentially correlations and probabilities for certain parameters. The second type of modeling, inverse modeling. I'll call it here as well point-in-time modeling. Why do I do that? It's because inverse modeling is sort of a very broad term and can sometimes be used quite differently depending on the scientific field. But in this case, what we mean is we are trying to constrain the structure of the star. Well, not necessarily the structure, could be the rotation profile as well. So we're trying to constrain that, and not based on some evolutionary physics, but just trying to figure out what is the star doing right now. That has the advantage that you're not constrained by that evolutionary physics at all anymore. You don't have any issues anymore where if you have unknown physics in your evolutionary process that you are not able to properly capture the observations anymore. But of course, that means that you also have a constraint less. If you say, I want my star to be, I want to be able to evolve my star up to this point, that's an additional constraint. So typically, if you do an inversion, you might get more degeneracies. You might have more options for your internal structure than you would get with forward modeling. And yeah, so you may be less good at actually constraining your parameters. Here is an example of that. It's a very simple rotation inversion. Some might not even call it an inversion. But the idea is that you have multiple modes. There are 3 indicated here. 2 of them are G modes. They have their peak close to the core, and one of them is a P mode close to the surface. These functions here indicate how sensitive the modes are to the rotation frequency at a certain point in the star. So for example, our G modes are most sensitive to the rotation frequency in this region. The P mode is most sensitive to the rotation frequency in this region. What you then can do in this, well, what was done in this case is that you, for example, say, okay, I have 2 free parameters. the rotation frequency at the core, the rotation frequency at the surface. And what we're then doing is we're fitting that, and we're fitting that in this case with multiple possibilities for the transition region between the core rotation rate and the surface rotation rate. So for example, the blue one, there it's in the envelope. So the transition region is over the entirety of the star. For the purple one, the transition region was chosen very close to the core. And you can see that gives quite different results, and that's also what these degeneracies are that I was talking about. You have much more possibilities for your rotation profiles than maybe you would have if you would evolve your rotation profile from the birth of the star. So, but with these kind of techniques, you can, from those sensitivity functions, from the observations, you can then try to figure out, okay, what is my rotation profile of my star? So that's the main idea of an inversion, is that you go from some observables directly to the properties of the star. There are more complicated ways to do inversions. This was a very simple profile. You can also have more complicated profiles with more parameters, sometimes even, as we will see later as well, with more parameters than you actually have observables. You can say, how do you even fit that kind of thing? Well, you can penalize certain profiles if you say, okay, I don't want too much variation. I don't want the profile that's really jagged, that you can penalize for via some regularization functions. Another method is rather than saying, okay, instead of giving me a full profile, I just want to try to see where in the star can I actually constrain something. And that's what this optimally localized averages family of techniques is doing, is just saying, okay, at a certain point in the star, can I get a value out of it? And if so, what is it then? And what is sometimes also done is that rather than starting from 0, you can also take some model you got from forward modeling and try to see how do I need to change this model in order to match the observations. All right, so that sort of was the introduction. Let's go to the main topic of the seminar, which is this star, AG192575, and I'll show you how we try to obtain the rotation profile of this star and the magnetic field properties of this star. So AG192575, what is this star? It's a B-type star, 12 solar masses, and it's near the end of its main sequence. So you can see here the core hydrogen fraction is already quite low. It's a beta-Cepheid pulsator, and it was modeled by a former PhD student here at the IvS, by Simon Bursens, just last year at the end of his PhD. What makes this star interesting? It's, for me at least, it has a mix of G modes and P modes. That means it has modes which carry information about the near-core region of the star and modes that carry information about the surface of the star. That allows you to sort of recover properties over the entirety of the star, which will be very useful once we're going to look at the rotation profiles. The second thing that's interesting about this star, it has multiple rotationally split multiplets with asymmetries. I assume that for most of you, this sentence meant nothing. So I will now go through this sentence and try to explain this. So if we want to know what a rotationally split multiplet is, we need to understand how rotation affects the pulsations. Let's start with a non-rotating star, right? So picture you have a sphere, and there is a pulsation going on in that sphere. If you then choose some axis through that sphere, right, that will be the rotation axis later, then you can essentially split your pulsation into 3 components. Well, 3 types of components. You have one component which is symmetric towards this axis. That's what's shown here on the left. You can see that the pulsations, well, the colors here indicate the phase, and you can think of them as the colors constantly switching in time. That's the pulsation. So that's the one on the left. That one is symmetric. You also have the possibility that some of the components will rotate in one direction, others will rotate in the other direction. Those are the 3 types of components. And you can see an example of such component here on the right. So this one, the colors are just switching. In this one, the colors are actually not really switching, the thing is just rotating. So that's the second type of component. We have symmetric, rotating in one direction, rotating in the other direction. Those are the three types of components you will get. Now, in a case of a non-rotating star, you could put this axis in any direction. So what you will get is that these components will be completely indistinguishable. They're completely degenerate. They will have the same frequency. However, when we add rotation on top, so if, again, you take your star, if we add rotation on top, for the symmetric component, nothing will change if you start rotating. However, if you take one of the components that's rotating in this direction, and you add rotation on top of that, from your point of view, you will see those blue and red regions come by faster, so its frequency will increase. For the components that were rotating in the other direction, if you add rotation on top of that, then the frequency of those components will decrease. And so we get something like this, where we have our 0, so that's our symmetric component. It is not shifted by the rotation at all. We have components that are moving in the direction of the rotation, so their frequency is increased. And we have components which were moving in the opposite direction of the rotation, so their frequency will decrease. And this difference here between those peaks is, well, in this case, almost constant, and is proportional to the rotation frequency. So the higher the rotation frequency, the broader these multiplets are. So these are our rotationally split multiplets, which was the first part of our sentence. It's slightly more complicated than that. There are two effects we need to take into account. The first one is the Coriolis acceleration. So if your stars start rotating, the way we described it just now assumes that your physics remains the same, which is not the case. In a rotating system, you get a Coriolis acceleration. And the second aspect that we need to take into account, I already showed these sensitivity functions. Well, we do have to take this into account because, let's say, your star is differentially rotating. It's rotating faster in one region than in another. Then, let's say it's rotating faster in the core. Then your G-modes will be, the splitting of your G-modes here will be broader than the splitting of your P-modes. That's luckily also an advantage because that means that we can really try to drill down and figure out, okay, here near the core of the star, what is the rotation frequency versus the surface of the star? So that's the part of the sentence about rotationally split multiplets. In this star, there are multiple of them. This is the frequency spectrum in top. So this is just based on if you take the whole light curve of this star, which has been obtained by the TESS satellite, then do a Fourier transform, you get something like this. And these boxes correspond to the 3 panels below. And you can see in this case, I have indicated 5 rotationally split multiplets here. There are more in this star, but these are the ones that we could actually do something with. I'll show you the frequencies here and the splittings. So these are the G modes. These are the P modes. And you can see all the frequencies. These are not too relevant. But more interesting is the spacing. And you can see, for example, already the G modes here have a higher spacing than the P modes. So you may already infer from that that near the core of the star, well, it's rotating faster near the core of the star than near the surface. But what you may also have noticed already is that these spacings are not exactly constant. They're almost constant. There is a bit of difference between them. And you can see as well, these are the errors that are indicated there. These asymmetries are larger than the observational errors. That means that they are probably caused by some physics. And this physics is very interesting to us because we can use that to constrain certain things of the star. So how do we interpret these asymmetries? Well, the first element is, again, rotation. The fact that rotation leads to nicely spaced multiplets, that's only a first-order approximation. If you take your oscillation equations, you compute your frequencies with a tool like Gyre. If you add then rotation to that and you do a first-order approximation, you get symmetric splittings. However, if you go to higher-order approximations, you may get asymmetry. Your rotation will also deform the star. That deformation, that flattening of the star, can also cause asymmetry in your multiplets. And finally, magnetism can also cause asymmetries. So that means if we have asymmetries, that we may be able to learn something about the magnetic field of this star. right? Because different magnetic fields will give different asymmetries. So we have this opportunity to constrain the magnetic field of AG192575. There are some challenges associated with this, however. You see, I explained it, the arrow from rotation to asymmetry. If we want to interpret the asymmetries, we also need to know what the effect of the rotational effect is on the asymmetries. And in this case, the rotation and magnetism have a similar effect in the sense that the magnitude of the asymmetries for both cases is almost the same. We also need to compute these higher order effects of rotation. That requires a little bit of, well, a little bit more annoying math. Stellar deformation will also need to be taken into account. And the final thing, if I go back to these modes here, we also need to know what these modes are. What are the properties of these modes? And you can try to figure that out by doing forward modeling. You can try to see which frequencies in your stellar models match the observations. But in this case, we have multiple possibilities. And that's an additional uncertainty we also need to take into account. So in this case, we have essentially 8 sets of forward models where we have 8 different identifications of the oscillation modes. And I put the cutoff at the 100 best models for this work, and we have around 700 to 800 stellar models that we will take into account for the determination of the rotation profile of this star and its magnetic field. So how do we actually solve now the problem between rotation and magnetism? The first step is we're going to use the symmetric component of these multiplets to do a rotation inversion and obtain the rotation profile. This works in this case because they are almost symmetric. The higher order effects of rotation are not really affecting the symmetric component of this profile. You already saw the asymmetries were quite small compared to the overall splitting on the order of a few percent. With the rotation profile, we can then compute, with an approximation, we can then compute the higher order effect of rotation and obtain the asymmetries due to rotation. If we then subtract those from the observational asymmetries, what we're left is, we assume, due to a magnetic field. So in this way, we can subtract the effect of rotation and obtain the properties of our magnetic field. The first step is therefore to do a rotation inversion. What do is we parameterize our rotation profile as a linear combination of these functions. These are splines, and you can see they're already quite smooth, which is quite useful if we want to do calculations later with them. However, you can see there's quite a lot of functions. There's 10 to 12 here. I don't know the exact number by heart. But that's definitely more fit parameters than observations, because you saw we only had these 5 oscillation modes identified. And so we only have 5 symmetric splittings. I have much more functions here. So therefore, we will be regularizing these profiles. We're going to say, OK, I will penalize my rotation profile by how much it varies. So a strongly varying profile will be considered less good than a more straight, more smoother profile. Again, we have multiple stellar models. So for each of those 750-ish stellar models, we will have a rotation profile. So in the end, we'll end up with 750-ish rotation profiles. And in an ideal scenario, they will all be the same. They are not. You can see here, these are the rotation profiles for the best model out of each of the possibilities for the mode identification. And some of them are relatively nice. If you look at the one indicated here by original, so this gray dashed line, you can see it's fairly smooth, it's fairly nice. It doesn't vary too much. It has a bit of a bump in the middle of the envelope, but overall, it's pretty clean. But if you look at this black one, it starts up here, which is around a period of 2 days. So the core of the star rotating every 2 days. It goes all the way negatively, meaning you would have an envelope that's rotating in the opposite direction. And then it comes back up, and the surface of your star is again rotating in the same direction of the core. That is pretty unlikely. So what we could say here is that perhaps this stellar model is probably not a good stellar model. It probably doesn't match reality as much as the others do. But the issue is, in that intermediate regime, for example, this red one, this other gray one here, these don't vary as much, and it's difficult to say which ones of these rotation profiles is actually the correct one, or at least the least wrong rotation profile. So that's a major uncertainty, because you can see the areas around the profiles are the observational uncertainties. The mode identification, so the uncertainty from the mode identification will be much larger than the mode identification of the uncertainties of the observations. But let's for now keep these rotation profiles and move on to the next step, which is computing the asymmetries. In a first-order approximation, as already mentioned, you get symmetric splittings. What you essentially do is you look at the difference between your non-rotating frequency and your frequency, and that's proportional to the rotation profile multiplied by the sensitivity function, right? And that's integrated over the star. And this m here indicates which component of your pulsation mode you're actually talking about. So this was this -2, -1, 0, and so forth you saw in the plot earlier. And yeah, this gives symmetric splittings because this part is the same for every of those components. So you get just nicely, this differs by 1 for each mode. However, if you want to look at the asymmetries, we need to do a higher order approximation. Yeah. The way we do that here, I will not go into the details of the math, then the seminar would be much longer. But the main idea is that rather than this just takes into account the information of one of the oscillation modes, is that you can combine the information of all the oscillation modes and fit your frequency, well, you solve the oscillation equations again with those combination of multiple modes, and that gives you the asymmetries. There's, however, a big challenge, and that is stellar deformation. Again, as already mentioned, when you have rotation, your star will flatten out. Rather than being a sphere, you might get something like this. That modifies the stellar structure, that modifies the oscillation equation, and you need to take that effect into account if you want to properly know what the asymmetries are of your splittings. The way we currently do that is by using this third-order approximation, a bit modified. But there are formulas for that, and we can implement them. However, the results don't match with reality. I get asymmetries, at least with this method and with my implementation, where the values range from 20% asymmetry to more than 100%. What do I mean by that? 20% asymmetry would be that one of, let's say, this peak would be shifted over by 20%. 100% would mean that they start to swap places. You don't see that here. This is just by looking at this plot, you can see that these are almost equally spaced, and therefore that something is wrong with this. At this point, we don't know yet what the main reason is behind that, if it's either the way the approximation works, which could be the reason, or my implementation, hopefully not. But for now, this does not match reality at all, and we can't really use that. So we will, for now, exclude the effect of stellar deformation on our calculations, even though that's not, in the end, that's not the right thing to do, but it's the only thing we currently can do. Final step is then to figure out what the magnetic field is doing. We have computed our asymmetries from our rotation profiles. We have subtracted them from our observed asymmetries. And the next step is then to look at our magnetic field. When you have pulsations, your magnetic field lines will be dragged along with those pulsations. And due to that, the magnetic field would also have an effect back on the pulsations through the Lorentz force. And so you need to include your Lorentz force in your pulsation equations. And again, this can be included in a sort of a perturbative way, just like with rotation. The field we're using is a dipole field, so it's sort of the simplest magnetic field you can have. But there is a component of both poloidal fields and toroidal magnetic fields, just to ensure that the field sort of remains stable. And you can see here an image of a dipole magnetic field. So this is from the Earth magnetic field Right. With that, we can then compute the asymmetries due to a magnetic field. There's two parameters that we have. First of all, the inclination with regards to the rotation axis. You can see it here in the image as well. Your magnetic field axis does not need to be aligned with your rotation axis. Secondly, the asymmetries will scale with the square of the magnetic field strength. So that's our second parameter. And in this plot, you can see this is a plot for one magnetic field strength. The colors indicate the angle between the magnetic field axis and the rotation axis. The black dot is aligned. The yellow is 90 degrees. So what we find here, so this is for different oscillation modes. You have low order G modes here, low order P modes here. And for example, you can see, okay, the effect on these P modes here is much stronger than the effect on the G modes. And if we have a positive asymmetry, then we're dealing with a field that is slightly inclined with regards to the rotation axis. If we have a negative asymmetry, then our field is strongly inclined with regards to the rotation axis. And this can then be fitted to your observations and get out a magnetic field strength. That's what is shown in this plot. For each possible value of so the obliquity is the angle between the rotation axis and the magnetic field axis. And for each value of the obliquity, we get possible magnetic field strengths. So this is, you can see here, the colors are by the number of models. And you can see here this nice increase. That's because as you go to a certain angle, it's around 55 degrees, the effect of the magnetic field strength of the magnetic field on the modes drops to 0. So it bumps up the magnetic field strength in order to actually match the observed asymmetries. You might wonder, why are they all on this side? Why is there nothing on this side? Well, that's because in the observations, the remaining asymmetry that needs to be after the subtraction of the rotational asymmetries is negative. So for most of the models, that means that you will need to have a magnetic field that is more inclined with regards to the rotation axis in order to fit the observations. But otherwise, there's no constraint that tells you apart from, let's say, having 90 degrees obliquity or around 55 or more. To have a better view at this, let's look at just the magnetic field strength for the 90 degrees. That means if your magnetic field is perpendicular to your rotation axis, that's the case where you need the least magnetic field strength. And also, since most of the models require negative asymmetry, that's the most interesting part to look at. As you can see, we get quite a wide range. We're going from only around 10 kilogauss, so these magnetic field strengths are in the core of the star. If you would have that at the surface, then that would be massive. But all the way up to almost 200 kilogauss, which is quite strong. So at this point, there's still quite a large range. So one more thing is we also really would like to know, okay, if we fit our magnetic field, is it actually reproducing the observations? The answer is sort of. If you just look at how the magnetic field, adding the magnetic field improves with regards to the frequencies, the asymmetries corrected with the rotational asymmetries, then you see that around, for most of the models, this essentially says around 50% of the asymmetries are explained by, for 80% of the models, by the magnetic field contribution. There are somewhere it's higher, somewhere it's lower. But if you combine rotation and magnetism, so if you just go from the observations, subtract rotation, add magnetism, see, okay, how does that compare to my original observations? Well, then you see that we, in most cases, end up with more asymmetry than we started with, which is not ideal, and that has to do with the fact that essentially, if you have asymmetries, rotation will push it positive, and magnetic field needs to compensate all the way for that. And that's sort of like you get this cancellation, and then it's difficult to really improve on your initial observation. So most of the effect of the magnetic field most of the fit comes from the fact that you added this rotation component. So for this part, Can we constrain this magnetic field? Yes and no, in the sense that yes, we can put values on the minimum and maximum magnetic field strength in the core, given all of our assumptions we did. But we do, before we can actually say we have properly constrained it, since the range of values is quite large, we need to have a better handle on the mode identification or the forward modeling. We need to include the effect of deformation, because who knows, if you actually properly deal with that, how much that will shift your asymmetries. And other field configurations could also be interesting to look at, mostly to see if you can have a better fit with the asymmetries. All right, so that was it for the part on the magnetic field and the rotation profile of AG1 and 2575. Oh, yeah. The final, let's say, dessert of this seminar will be my ongoing work on structure inversions. So to bring up the slides again, what we're trying to do is figure out the structure of the star at a certain point in time, namely how it is now. And we are interested in G-mode pulsators, and for that, it's most relevant to look at the buoyancy frequency. What is the buoyancy frequency? The buoyancy frequency essentially tells you if you take a fluid element in the star and you would displace it from its position, it would oscillate with a certain frequency around that starting point. And that's what the buoyancy frequency tells you. And that's also why the buoyancy frequency is so much linked to the G-modes, because this oscillation is essentially restored by gravity, and that's also the restoring force of the G-modes. So if you know the buoyancy frequency, you can almost completely calculate how the frequencies of your G-modes will behave. The buoyancy frequency, here indicated by the buoyancy frequency squared, is also relevant for another reason. It is linked to the temperature gradient in the star and the mean molecular weight. Now, that last one is very interesting, because the mean molecular weight essentially is determined by our hydrogen mass fraction. So you can see here, this is the hydrogen mass fraction. It's almost constant in the convective core, since the material is very much mixed there, and then increases up to the surface. And this region here is where the convective core has been retracting over the course of the evolution of the star. And the shape of this region, so how fast this goes up and in which way, that is very important for stellar evolution, as it essentially determines how much energy how much hydrogen the convective core has taken away with it, has been used, how much it has available, will determine the lifetime of the star, amongst many other properties. And you can see here as well that at that point there is this peak in the buoyancy frequency, and that's, yeah, so you see that's the mean molecular weight gradient. So determining the buoyancy frequency can tell you a lot about the evolutionary history of this star. In order to do structure inverse, we can basically start with doing the same thing as with rotation. We look at how our frequency changes if we change our buoyancy frequency. And again, we have here this sensitivity function, which again depends on a single mode. And so you can say, okay, if I want to know this buoyancy frequency here, this difference, then I just need to fit the buoyancy frequency to difference between my current model and the observations in terms of the oscillation frequencies. However, that does not work. In this plot, I show if I compute an evolutionary model, so a MESA model, I have two of them. I have a reference model and a target model. And with this equation, so I have a difference between the two models because I just computed them, I can look at, okay, how does that change the frequencies according to this first order approximation. So the reality is indicated by the orange line and the gray dashed line. What the approximation does is the blue line. So the approximation is worse than if you would just take the original one and say nothing has changed. That's not ideal. The reason for that is that as the star evolves, at certain points for certain oscillation modes, they start changing quite rapidly. So this plot shows the core hydrogen fraction, so the star is getting older here. Every line is one oscillation mode, and they're a bit pushed together, because otherwise the plot will go all the way up. And you can clearly see that there are these regions, lines going down here, where the oscillation mode is changing quite rapidly. And that's what we call an avoided crossing. Essentially, what's happening there is two oscillation modes that are sort of close together. They will look like this if you evolve, right? So they will sort of appear to be pushing away at each other. And at this point, the structure of an oscillation mode, this shows this is the radial coordinate, so the position in the star. And this is just how the displacement is going. It's going one direction, other direction, one direction, other direction. That's essentially what that is saying. And you can see here at this point, which is close to where we are here, there is quite a large difference. So the oscillation modes start changing quite rapidly. And that breaks our linear approximation, which assumes that the oscillation modes aren't really changing much at all. And that's the reason why, if I go back to this plot, is the reason why we get this super bad approximation. So how do we fix that? There are sort of two, let's say, two things that I know of. One option is to, rather than doing an approximation, you just say, OK, I'm going to take my changes in the stellar structure of the star, relax my cell model again, push it again through a full oscillation code, and recompute the frequencies in that way. That will give you, again, the exact frequencies that you would expect. What I've been working on is if these mode properties are mixed, so essentially what's happening here is that the properties of different adjacent oscillation modes, so you can see here, like, for example, these two here next to each other, if you would plot these functions next to each other, you would sort of see one of the oscillation mode becoming the other and vice versa. So essentially, the properties of the different oscillation modes are mixed. And so maybe in order to solve this problem, we can try to mix the oscillation modes. So what I'm doing is similar to the rotation asymmetries, where I also combined multiple oscillation modes, is I'm combining here, again, multiple. So this is, instead of having just one oscillation mode in my approximation, I combine multiple. This gets then just plugged back into the oscillation equations. We have to then solve for the frequency, these parameters. That just takes a bit of math, but it's not too difficult. This is the result. You see again here the same three colors we had before, but now there's a new one. This is the new methodology. And as you can see, this black, brownish line follows the gray line much better. So, and it's a stark improvement compared to this blue line, which was completely all over the place. So what does this mean? This means that we now have a methodology to properly predict frequencies starting from a reference model and a difference with a target model. That means, of course, if you can go one way, then the only thing you need to do is go the other way. This is no longer a linear relation. So the function you saw before was linear. So we cannot use something like linear least squares to just fit the buoyancy frequency, but instead we have to do something more complicated, for example, some MCMC-based sampler or other sampling methods to have to fit your buoyancy frequency profile. But that's currently ongoing work. That's something I'll hopefully not spend, hopefully won't take too much time to actually implement, but we all know how reality goes. But with that, I'll leave you with the two conclusion slides together, and I'll be happy to answer your questions.
Thanks, Vincent, for an interesting talk. We have enough time for questions.
Hi, Vincent. Thank you for the talk. I have two questions. My first question is a few slides back where you said that you wanted to combine multiple displacements. What are the AI components? Do we know them, or is it fitting values as well?
This is just essentially free parameters. This is just a linear combination. These are coefficients. The main thing we're doing, I don't know if I have a somewhat more, a slide that slightly explains this better. So this is for rotation, but the idea is very similar. So what we're doing is we have this linear combination where these AI are free parameters. And what we're doing is we're essentially plugging that back into the oscillation equation, right, which is just Newton's second law. And then we integrate this equation over the star. And if you plug that all in, you get a matrix equation that looks something like this, where we have the oscillation frequency as a parameter, and all these A. This is just an eigenvalue equation at this point, with just matrices, with just values, and you can, with some transformation, because it's a quadratic eigenvalue equation, you can solve this with the usual eigenvalue techniques, and you get eigenfrequencies, the omegas, and your eigenvectors, which will be these A's.
And does it tell you something physically, the values of these A's?
Well, in a way, yes. It tells you, if you fill that back in here, you can say, okay, in my modified star, my displacement function for the oscillation modes will be this linear combination.
Okay, thank you. And my second question is on slide, I think, 15 or 16, where you showed the observed coupled modes.
Mm-hmm. Yep.
For the right figure, the, I guess, yellow pulsations, they look quite small, especially the -2. I don't really see it.
Yeah.
How do you measure them or know that this is actually a mode and not just noise?
Once you, so what we typically do is we have some criterion to select a peak. Then we fit that to the data and remove that from, we subtract that from the data. And then this entire peak with its side lobes, because this is actually also part of that single frequency, that will just disappear out your frequency spectrum. And these smaller peaks will become much clearer.
Okay, makes sense.
Hey, so thanks for the nice talk. For the rotation inversion, you ruled out one of the models because it was like, it could mean it's unphysical, the rotation inverts toward the star. So in this case, can you rule out everything which is doing rotation inversion, or there could be still possibility for some rotation inversion?
So at least for, so this is just, I haven't like ruled it out in the sense I completely discarded it. So I'm still using it for later calculations. But just if you want to have an idea, okay, if you want to have an answer to the question, what is my rotation profile? Then this one is probably not like it. It's probably more like this. But much other will be difficult to really rule out, just purely based on, also because we don't really understand at this point fully how the rotation profile evolves in a star. There are many different effects that play into that. You have all sort of circulation that evolves. You have waves in a star can also transport angular momentum. And at this point, that's still like, how all these factors combine is still unknown.
Yeah, and I have one other question. It's probably a little naive, but for the magnetic field strength, can you apply your models to main sequence stars? So this is like out of the blue question, huh?
Yeah, so this star, AG192 2005, is a main sequence.
So this is a main sequence star?
Yeah.
I thought it's a massive star, no?
So it's near the end of its main sequence life.
Okay.
It has a correlation fraction around 0.17,
Okay.
but so it hasn't reached the end of the main sequence yet.
And then extrapolating on that, can you also apply it to like a G-type solar star? Probably
well, if you have the asymmetries, if you have the modes, at this point, nothing in this analysis, at least from a theoretical pulsation standpoint, depends on what type of star you're looking at. I don't know how reasonable it is to, for example, make this assumption for the magnetic field. That might be another aspect that's... Yeah.
Okay. Thank you.
Hi, Vincent. Nice talk. You mentioned that you are currently not incorporating stellar deformation in your work because it adds quite a high degree of complexity. Are there any ideas currently for how you might go about incorporating it into your work?
Yes. So the main thing, because these approximations are not working, are not seem to work, and I can't find any mistakes in my code, the main thing that we still have to test at some point in the future is try to not do it with approximations, but actually with stellar oscillation codes that can do essentially can take into account the flattening of the star completely. And that would at least give an idea of whether the approximations are wrong or whether something else is really going on.
Okay. Hi, Vincent. Thank you very much for that. Could you go to slide 38, I think it was, where you're comparing your predictions to...
Yes.
There we go. So you have this lovely match between your black prediction line and the target line below a period of 2.5-ish days, but above that it starts to get, you have some small mismatches.
Yes.
Why is that?
Yes, thank you very much for that question. That's very interesting. I'll go back to this. I cannot put an infinite amount of oscillation modes in here. I only have a finite amount I put in here. In this case, it's ranging from n equals 0 all the way up to n equals 120 G modes. So there's 120 modes behind this calculation, which means this goes on further. I have purposefully cut it here, because if you go further, that suddenly whoop, starts doing all weird things. And the reason for that is that the closer you get to that edge of your modes, like of your set of modes, the worse the approximation is, because it also needs contributions from even higher order G modes to properly describe what's going on. And you can see the beginning of that here, where it sort of starts deviating and starts to become all jaggedy. So it's just the fact that we make a cutoff in the approximation. That's what's happening here.
Hi, Vincent. I was a bit surprised by the rotational profile that went negative. Is there no regularization in your code that would prevent this?
So this is a regularized profile. But the reason, so what I'm doing is, so you also always have a tuning parameter that tells you how much should it look at the observations, how much should it follow the regularization. And I chose the tuning parameter such that we're still sort of explaining the observations, because that's what we want to do, that's our goal, but still make it as high enough as possible. For this profile, it turns out that you need that tuning parameter to favor the observations much more in order to get something that actually fits. So this is just an indication that if you take this stellar model at face value, you just need a complex rotation profile in order to explain the observations, which might indicate that this stellar model is not as great as you might think.
Okay, I have a second question in mind. Would you like to have more precise frequencies, or would you have to like more of them?
Neither. I would like to have more identified frequencies, because there's a lot of frequencies in this spectrum that we don't know what they are. We know them precise, but we just don't know what they are. And it would be extremely awesome to know what these actually are, what the properties of these are, so we can get much better constraint on both our forward modeling and our rotation profile. That would be the main thing.
Following on to that, Vincent, can you I should know, but I have forgotten. Have you used 3 years of test data as a baseline, or 5 years? And what would you need ideally to, aside from assuming that you can identify, how would like an 8 or 10 year test light curve help you, if at all?
The main thing it would help you with is actually for this specific multiplet, if we go for a very concrete thing, is you see these are very much overlapping. And one possibility for this is that it's not 2 multiplets overlapping, but it's 1 multiplet split by rotation on top of split by magnetism. So what magnetism can do in principle is that it takes the splittings of rotation and splits them even further. So if you would have a much longer time series, you'd be able to, maybe more frequencies would come out of the noise here. And that would help you either confirm that this is something magnetically split or something else. I think so. I don't know by heart.
Yep. Hey, Vincent, thanks for the nice talk. don't think I've ever seen the word wind appear in another astroseismology talk. So I was just wondering, could you comment on the effect of winds in your talk? I just saw it in one of the first slides, and I was just
I made a mistake there, I think.
Curiosity was piqued. Yeah. Thanks.
Yeah. So at least for so most of the effect will be on the evolutionary side, I would assume. But yeah, it's not really, I think, a parameter we play much with, at least in our team. But yeah, would be maybe something interesting to look at, like how does my constraint change when I change the wind prescription, for example. I know depending on the star, your winds might start blocking out the pulsations or something like that, but as far as I know, that's not the case for stars like this.
Hi, Vincent, thank you for the talk. A few comments. For the p-mode asymmetry, I think the most dominant term is from the second order perturbations. It's from a stellar deformation, so it cannot be ignored. And if you ignore it and fit it only with the magnetic field, you get a very inclined magnetic field, because you shouldn't only fit the magnetic field to a positive asymmetry. If you fit both rotation and magnetic field, it should work. And second comment is another factor, which is the rotation split three-mode coupling. So the L equals 1, L equals -1 can couple to M equals 0. And this kind of third-order nonlinearity can cause phase locking, which can enforce the equally spaced splitting. And it can also in the region of modulation. So it's, it means there's some other factor you need to consider. So it should be more complicated. This asymmetry should be explained by many different reasons, not only by 2 or 3.
Yeah, absolutely. There's definitely, I know that's basically why can we constrain the magnetic field has both a yes and a no, because yeah, definitely the effect of deformation is not taken into account properly. That I assume that if once it's figured out, that will definitely have an effect on what magnetic field properties we get out. And yeah, so especially one small remark is that since these are very low order P modes, the situation is, yeah, so these are very low order P modes. The situation is slightly more complicated in the sense if I do this coupling, it's sort of you have the asymptotic P mode regime, and then there is what I find in the asymmetries is a peak around the mixed mode regime, and that these all fall into this, and that's the main factor what makes it so difficult to really analyze these is that fact that they are in the mixed mode regime. But yeah, one other thing indeed is also missing is the coupling between the different values of L. That would also be interesting to add, but that's sort of part of the same solution. If you run, if you solve this with a 2D oscillation code, you typically also already get the couplings between the different degrees of L. So that would be interesting. Okay, right.
So maybe guys, you can continue discussion at the lunchtime. So the very last question here.
Hi, brilliant talk. Just a quick question, because you said you don't include deformation right now in your modeling, but I was just wondering if you have any observational constraint for that specific star on how stellar deformation due to rotation might affect it. Like you're on the right slide right now. Do we know if it's a fast rotator and we expect a lot of deformation, or?
Yeah, so the deformation is not massive. It's not like these stars, because I think it's around 20% of the classical critical rotation rate. So there is some deformation, I think on the order of a few percent, but it's not this level. So I don't know, yeah, depending on also the brightness and as such, I don't know whether it's really observable to directly constrain the deformation from like interferometry, for example.
All right, we are at the hour. Let's thank Vincent again. And thanks to everyone for coming, lots of activity, and I'll see you next week.